Many thanks to the co-chairs, Renato and Tobias, for inviting me. It is one of the greatest honor. I'm very grateful to Bob's kind introduction. I'm totally humbled. My talk is not really about my work, but about how to understand and explain the wonderful work done by all these colleagues. This year, the VIS conference introduced 6 areas. Patrick and Christopher in the revised committee collect and analyze some data and estimate the possible distribution of the submissions in the 6 areas. As you can see, number 1 is applications, and the number 2 is area 1, theoretical and empirical research, suggesting the importance of this area. I saw some numbers suggesting that the estimation reflects the reality reasonably well. At least the order of number 1, number 2 seems to be correct. If we consider area 2 to area 6 are practice, the balance is perhaps about right. Area 1 has 2 major sub-areas: theoretical research, including the topic of information theory, and empirical research, which has a strong connection with psychology. We often mistake that area 1 should guide the other areas. Because this is a young discipline, the existing theories are mostly suitable for making recommendations. Meanwhile, practice can provide the theories with positive and negative evidence, and it can question existing theories and suggest new hypotheses. There are also interactions between the 2 sub-areas. Theoretical research has a role to abstract, explain, and hypothesize, while empirical research can test the question and suggest abstract theories. In general, the goal of Area 1 is to explain all the works in other areas. Ideally, we have some good abstraction and measurement, so theories become useful to model, simulate, predict, and optimize in practice. We're not there yet, but we are scientists. We can and should always try. There are also interactions between the 2 sub-areas. Theoretical research can have a role to abstract, explain, hypothesize, while empirical research can test, question, and suggest objective theories. In general, the goal of Area 1 is to explain all the works in other areas. Ideally, we have some good abstraction and measurement, so theories become useful to model, to simulate, to predict, and to optimize in practice. We're not there yet, but we are scientists. We can and should always try. In EuroVis 2012, Thorsten gave a capstone talking about the SciVis and the InfoVis. His stimulating metaphor with the 2 Germanys, which raised a few very loud questions, such as, where is the visual analytics? Is InfoVis east or west? Perhaps let's consider some places on the map as our metaphor for theory and practice. Perhaps not. I do not have the same courage as Thorsten to be involved in geopolitics. We need to have more competition. I do not think we need unification, but the competition helps. And we all have practical experience and ability to observe and abstract. We all have theoretical voice and practical voice in our head. We should let these voices talking to each other and challenging each other. Perhaps let's start talking to Bill Bryson, who gave an interesting visualization challenge. Bill Bryson is a great and beloved author, and he explained his problem. If we reduce the Earth to the size of a pea, and Jupiter would be over 300 meters away, very big, and Pluto would be 2.5 kilometers away, but very small. And how could you visualize the solar system correctly to the scale? As you can see, the planets in the solar system have very different size. In comparison to the Sun, many of them are tiny and almost invisible. The 4 planets close to the Sun have a very similar distance, and in comparison to the other planets, which seems moving away very fast from the Sun. If we were picky, it is easy to criticize these visualizations to be incorrect. 30 years ago, when I was working only on cyber problems, to me, visualization was just about encoding. When I started working on video visualization, I'm becoming interested in the mind and the decoding. I was told to use the study papers and I have to be submitted to the EuroVis. When I joined the area of visual analytics, I realized this has to include decisions and knowledge. Bill Bryson's challenge is about accuracy in encoding, and the psychologists have told us that decoding and what's after decoding is not accurate either. So if we can understand and explain the inaccuracy in viz, we may understand and explain inaccuracy in perception and cognition, or vice versa. Information theory is about encoding and decoding. The word encoding is often used in psychology too, and we can see the similarity and the difference among these two basic models. The encoding process in visualization is fundamentally a subset of what is considered in information theory, and the visual imagery is just a special case of signal. The perception and cognition in visualization is a subset of what is in psychology. As long as we can generalize the meaning of data and we can figure out a way to unify the term encoding and decoding. Let's have a look at the inaccuracy in human perception and cognition. Visual search can be fast or slow, and sometimes not very accurate, such as searching for a pattern. Gestalt grouping allows us to think quickly and communicate quickly, but it may cause illusions. Selective attention allows us to focus on important matter, but it has a side effect of inattentional blindness. Heuristics are models built from data and allow us to have a fast responses, but it may have biases. Most people do not have photographic memory, so our memory representation are abstraction and simplification, addressing the limited bandwidth, and we will have memory errors. All this because the process involved resulting less data, and hence we are losing information, and that becomes the cause of the errors. In other words, losing information is a fundamental in human perception and cognition. Ambitiously, I hope, if the information theory that we have formulated, and I'm going to talk about, can it explain this, and it may also applicable to this phenomenon in psychology. In this, we often say, give me a data set and let's visualize it. And information theory asks us to think about a whole data space. That's all possible data sets. It also asks us to estimate the probability of each data set. Similarly, after visual encoding, we consider a data space for all visualization images. After visual decoding, and we may consider all mental representations. After cognition, and we may consider all decision options. We can see that the general trend of decreasing entropy and thus losing information. Losing information is a negative term. It cannot be all negative if our mind is like that. And later we're going to see statistics, algorithms, and interaction all lose information. So let's consider both sides of the same coin. The good part and the bad part of losing information. We call the good part alphabet compression and the bad part potential distortion. All processes also have a cost. And if we introduce a subtraction and a division, we have a formula. My co-author, Amos Golan, and who is an economist specialized in information theory, named it a cost-benefit ratio. The cost-benefit ratio can have a unit of information for its numerator and can have energy for its denominator. Of course, the cost can be approximated by time cost and the financial cost. If we really want accuracy, we can just display and read all data values. And we will have a big space for our data visualization. And we will have a high cost for visual resources. And when we take in this information, which is also demand more time for viewing and more memory to remember. And because we have a limited bandwidth, error will occur. In order to analyze many data objects in our head, and we will have to incur a high cost of reasoning, and hence the possibility of a high error rate of reasoning. One best paper to be presented this afternoon shows the importance to consider the data space. The author, Andrew McNutt, argues that we need to test it against the possible data sets in the data space that may cause perception errors. Using Andrew's another relatively small data set as an example, we can see that if we want accuracy, we may just read odd numbers. Meanwhile, color and size perception cannot maintain the 3-digit accuracy, but is much faster. We always say this is data, task, and user dependent. This is correct. Information theory can explain this mathematically. Here I simply illustrate the mathematics. We can see that the information reduction depends on what data objects in the data space and their probability. If all possible data sets forms a huge data space, each visualization problem deals with a relatively tiny subspace. This is where normally write software differently for different visualization problems, such as volume rendering and text visualization. The way that information is reduced usually depends on the decision space that characterizes the task. If we have different tasks, and we may or may not need a different path. This is also user dependent because some tasks depend on the data outside of the data space. Human may capture knowledge from many sources and can use the knowledge in the current process of visualization. Externally, many of us often involve discussions with non-Viz colleagues and often have to make a case for Viz in relation to statistics, data mining, or machine learning. Statistics and algorithms usually transform the original data space to a smaller decision space quickly. The cost-benefit ratio fairly indicates the advantage of the machine-centric method, and that they can have a high information compression, low cost of viewing, and low cost for the memory bandwidth, and a low cost for reasoning. The main discussion point is always about the accuracy of information. Let's compare the accuracy between algorithm and the visualization. In fact, we would like to compare 4 different types of processes: statistics, algorithm, visualization, and interaction. It is now the examination season in many countries, and let's use examination as an example. Consider an exam returns n mark for n students. Our statistics professor computes the mean value and argues this is the best measurement. Our algorithm professor wrote a simple algorithm to find the min max values and argues that this is the best abstraction. Our visualization professor plots the n values in a bar chart, arguing this is the best mapping. Our HCI interaction professor argues that dynamics interaction with the database is the best. 3 professors can argue the accuracy of their method, but the visualization professor cannot. The bar chart can be used to calculate mean value, search for min max, and read each student's mark, but it is not accurate. The error measurement used by the other 3 professors is perhaps unfair to visualization. So with this, people would like to find an error measurement that is somehow equal to all professors. And when the 1 is only given the output value, and we ask that person to guess what the end marks are. Now we notice that none of them perform their task accurately, and now visualization can compete with other three professors on an equal term, and not about who is accurate, but about who is less inaccurate. This is the definition of potential distortion in the formula. Of course, the HCL professor may say that I can get all students marks, but other professors will ask, what is your cost? If we have a very long time series, we may use statistics to aggregate the data, but at some stage, users would have to see a plot, which reduces the potential distortion due to statistical aggregation. And if we increase the complexity of a program, at some stage, the program have to introduce some interaction. The complexity normally increases exponentially in relation to the number of lines, and we need interaction to increase the compression and to reduce the potential distortion. So this shows we can optimize between statistics and the visualization, and we can also optimize the algorithm and the interaction. And there are other optimization we can do. If a visual analytics workflow has 4 types of processes, our design objective is not to use this for the sake of this, but to optimize the usage of all these processes. In May last year, many UK colleagues answered a call for doing visualization for a group of COVID modeling scientists. Initially, 22 colleagues volunteered, and a few joined us later. Many of them spent many hours per week. Among them, Dr. Saiful Khan spent perhaps about 20 hours per week, and he was given an award by the Royal Society. Heidi Schumer, who examined the Saiful's thesis, may still remember him. The practical work in EuroVis challenges many theories and the guidelines in this. Here I just give one example, which is about dashboards. And it happens to be about the optimal integration between visualization and interaction. I've been looking for such an example for some years. And many dashboards display big numbers. And after a few months, the data points in each plot also seem to be too many. If we think only in terms of guidelines, we should always overview first. Displaying big numbers or truncating data seem to be undesirable. We all know Ben Schneiderman's information seeking manual, proposed in 1996. How can I use the information theory to show its correctness in 2010? Later, I tried to understand why my CFD colleagues usually prefer to see the details first, and the lizard team in Chicago also observed the same need. The mantra is correct, except many may not have considered that overview can take days and weeks and months. When this happens, the user may appear to want detail first. Hence, the mathematical proof was correct too. Of course, it is not easy to judge the optimal integration. Most optimization is done through a systematic process. David Ebert and I proposed such a methodology 2 years ago in EuroVis. We can consider the cost-benefit ratio for each process. Consider two options for display a few numbers or a summary plot in the dashboard. If the interaction cost is too high, and we can go find the cost in a previous or the current process. If there's not enough of one type of alphabetic compression, for example, user may have to use interaction to see key indicators. We can add more alphabetic compression showing key indicators, which can reduce the cost. We can also consider its side effects. I was involved in a two empirical study a few years ago. They showed that the viz has difficulty to perform data retrieval tasks against the tables, or estimating correlation indices accuracy against statistics. And then recently, Daniel and Karen's team showed that the accuracy of color perception is also unreliable. When visualization is compared with reading data and the interaction, and the viz has the advantage of low cost. When visualization is compared with the statistics and the algorithms, the visualization has the advantage of supporting multiple tasks. And in fact, statistics and algorithms are much more task dependent than visualization. In addition, visualization can utilize user knowledge to reduce the potential distortion. Many of us received our viz notification yesterday. Some of you may encounter a statement. This is an interesting paper. Experienced author may associate this with a rejection, while inexperienced author may be confused by such a positive statement. As we probably know, and in most cases, and it is associated with a rejection paper. This is how the knowledge can reduce the potential distortion, even the message is not quite what it means. Similarly, when we visualize a metro or underground map, we may see the equal distance showing on the map, depending on the various experience and with the metro map or the location, and we may reason the distance variation very differently. Hence, if we can assess user knowledge, and we can judge how much information we can actually lose. On Thursday, Matthias and from Statistical Netherlands represent a design space that focuses on how to lose information when a viz has to lose a fair amount of information. Information theory argues that visualization depends on data space, not just a few data sets. It depends on multiple tasks, not just a single task. It depends on users' knowledge. The task and the knowledge can also be modeled as data in mind by using information theory. The other best paper is on color. Let's very briefly remind you some major conversations in addition to the Daniela and the Karen's work mentioned earlier. Long time ago, Colin Ware showed that the multiband color maps are useful. The theoretical voice always tells us the rainbow color map is harmful. Perhaps we should use perceptually uniform color maps. But in practice, we just use color bureau most of the time, assuming it might be uniform. And in recent years, color semantics become an interesting topic. The other best paper is on the topic of semantics as well. I found much insight from reading the paper, and I can relate it to a book that I read a few years ago about the color words in languages. We should all read the paper, and after listening to the talk, if you have time, you will not be disappointed by reading the book as well. Color maps seem to be a small problem, but it really challenges our theoretical thinking. I was fortunately had the opportunity of working with Pascal and a few colleagues on this topic. The rightmost color map was created by a domain expert, which seems to violate many rules in a way worse than the rainbow color map. However, if we take the knowledge of domain experts into account, we realize that these color maps on the left do not contain enough semantics, which domain experts and will find the semantics really useful. So does it mean the color mapping rules are not useful? Pascal and the team did not think so. If algorithms are not accurate, we can still use them in conjunction with in-textual visualization. On Thursday, Pascal will talk about using somehow inaccurate the color algorithms in conjunction with in-textual visualization. Is this using visual analytics for designing color maps or other visual representations, perhaps? This goes back to the topic of quality metrics in theoretical research. We need more competition, and the four innovative young researchers created this visual guide platform for us to do so. Many colleagues have already supported their initiatives by contributing posts on the site. Please use them for our scientific conversation. Another four visionary young scientists, two started in visualization and two started in psychology. They created this workshop last year in visualization in this conference, hoping to shift empirical research from perception more towards cognition and to attract more colleagues from psychology to work on this. One of them, Darren, and I wrote this ISM article to encourage his colleagues to have a more conversation. And in the article, we mentioned two phenomena discussed by Roger Penrose, the recent Nobel Prize winner in physics. Penrose was fascinated by the human ability to prove theorems using visualization. Here's one of his examples. Hexagon numbers are sequence numbers that can be arranged in a hexagonal pattern. It starts with a 1 and followed by 7 and followed by 19 and 37, etc. The theorem says the sum of successive hexagonal numbers starting from 1 and there should be a cube. However, to prove the theorem and may require us to try to find a counterexample. If we fail to find a counterexample, and we somehow prove the theorem. And using visualization, and we can start looking at the first number 1. And then we add the pattern in a cubic form, but minus the first dot. We add another section and another section each time, and it gives a hexagon pattern on the bottom right, and it gives us a cube if we add all this all together. And this is how visualization is used to prove the theorem. Penrose tried to explain the mind using physics and mathematics. And of course, our visualization people will love such theories. And we can build our visualization systems just like a building bridge one day. And of course, our empirical study colleagues would like to test this physics hypothesis. And perhaps the theoretical researchers will still argue whether we should use information theory or algebra to be the framework. We should really focus on the outside of the biz. We should be able to explain and why this is useful. We should be able to bring psychology more into studying visualization problems. And we should aim to understand and be able to explain how this works, or then in some cases it may not work. Just like all other scientific and engineering disciplines, we can measure and model and simulate, predict and optimize visualization and the visual analytics workflow, perhaps one day. I believe we in this are currently at the right time and the right place to make a fundamental breakthrough and a paradigm shift. And we just need more conversation and more discussions and more questions. At this point, I thank you very much for listening, and more questions, please.